Hello, I built a breadboard computer based on basic ideas of Ben Eder and his fantastic video series, and I made some enhancements to his original design. And today's video is about the LCD display that I integrated into my system that allows to show some of the data in a more comfortable way than the original LED display with just one number. The LCD display I'm using has the name LCD 2004, which I guess comes from its characteristics, which is 20 characters per line by 4 lines. And this display also has a backlight, and I'm using the white on blue version. There are other versions out there, but this is the one I got. The board has a display controller integrated, which, like the name implies, controls the LCD display, and it handles the bus interface. So this is the point where data that I send from my CPU to the display is handled, and it also contains a character ROM so that all the letters and symbols are integrated in the display controller. The dimensions of that LCD display are good for integrating in a breadboard because the header pins that are soldered to that display have the perfect distance for putting it into a breadboard. From the hardware side, the display controller has an interface with 16 pin connections, where 2 of them are power and ground for the controller itself. So this is a 5-volt connector. There are 2 more power and ground connectors that are only for the backlight, which are also 5 volts. Then there is one additional connector which controls the LCD display contrast, and that should be connected to a potentiometer. Then there are 3 bus interface control lines and 8 bus interface data lines. The 8 data lines on the interface are meant to send commands or characters or font data. So this is data to define user-defined characters. And the 8 data bit lines, DB0 to DB7, define a single byte. And it is, like you expected, a line which is low to 0 volts is a 0 bit, and a high line, 5 volts, is a 1 bit. The first control line is the RS line, or register select line, which switches between command and data mode. And the command mode has features like initializing the display or clearing the screen or reposition the cursor. Whereas in data mode, you can send characters to the display which then appear on the screen, or you might send user-defined font characters over this data mode. The control line RS, register select, is low in command mode and high in data mode. The second control line on the interface is the read-write line, which switches between reading from the display or writing to the display, while writing may be a command or data, and this may be a display operation like switching on or switching off the display. It may reposition the cursor, so putting the cursor to the next line or to the home position, and it may be used to output a character or to send the font data. In read mode, the display can output its state, so saying whether it's busy or not, or if it's available for receiving data. And you can read the data which is on the screen, so you can read the characters from the screen, or you can read the current cursor position of the cursor on the screen. The read-write control line is low for write access and is high for read access. The last of the three control lines is the enable line, E line, which is used to start or end command or data processing, and it is low as long as the data which is presented to the interface should be ignored, and it is high as soon as the data on the interface is valid. The enable line is always operated from the CPU side and is always input to the LCD display. So a general bus write cycle, so writing from the CPU to the display, looks like this. First, you pull the read byte line low, telling that you want to write. Then you select the register that you want to write to, let's say command or data. And then you set the data to the data bits on the interface. And then you set the enable line high and low again. And that will tell the LCD that the data is to be read from the interface. The general read cycle looks similar. First, you have to tell the LCD display controller that you want to read data by setting the read-write line high. Then choose whether you want to read state from the commands or you want to read data from the screen. Then you put the enable line high, and a few milliseconds later you can read the data from the interface, and after you read the interface data you may or you must pull the enable line down again. The LCD controller has a special feature which allows the data to be sent to the display divided into two halves, while the typical 8-bit bus interface operates with 3 bus interface control lines and 8 bus interface data lines, which makes a total of 11 lines which go from the CPU to the LCD display, and thus allowing to read or write a byte per bus cycle from the LCD display, being simpler on the software side in programming access to the LCD display. There's another option which is a 4-bit interface, and that only uses 4 of the 8 interface data lines and ties the data lines DB0 to DB3 low. In this case you only have 7 lines going from the CPU to the LCD display, and thus you need 2 bus cycles per byte. So this is a bit more complex on the software side to send or read data to or from the LCD display. To connect the LCD display with my breadboard computer, I built a small LCD controller which interfaces between my CPU and the LCD display, and I use the 4-bit interface to save some CPU control lines. The data bus is in total divided into a upper and a lower part, while the lower part, the bits 0 to 3, are the data bits that go to the LCD display in 4-bit mode. And the bits 4 to 6 are the 3 control lines. And since there is one line left, I control the backlight of the display with the 7th bit on the data bus. So the whole LCD display is separated from the data bus, and so reading from the display or writing to the display is done through my LCD controller. There are separate CPU control lines, which additionally to the data bus control that controller. There is the LCD enable line, which is active low and which allows reading the controller data. And there is the LCD write, also active negative controller line, which allows to write data to the LCD controller. This is just a quick walkthrough the schematic of my LCD controller. The LCD display itself is that component on the right side here, and it is connected through those two registered chips, while the first register chip here in the middle has the data for the control lines, so the enable, the read write and the register select are held by the middle register chip, and the data lines DB4 to DB7 are held by that register chip on the right side. The register chip on the right side is controlled by the read-write signal, so that in case that the display is going to get data, so the write flag is active, the data is taken from that chip, and if the read signal is active, so that line is high, then that chip gets disabled, at least its output gets disabled, and the data is presented from the LCD display itself right through this bus transceiver. And this bus transceiver is active as soon as that LE control line is held low, and thus displays the data from the display and the data from the control register to the data bus, which is shown here on the left hand side. And in case of a write signal, so if write is active from the CPU side, the two register chips latch the data from the data bus, so the data for the display, the 4 bits of data for the display are taken from the lower bits of the data bus, and the control lines are taken from the higher bits of the data bus. And since the display only needs 3 bits for the control lines, the 4th bit of the second register chip would be unused, and so I used it to control the backlight on off for the display, so I can switch on and off the backlight of the display via a CPU control line. The ready-built breadboard with the LCD controller is this one, and you can see there is an additional capacitor under that LCD display for the controller logic, and there's the potentiometer right beneath it, and these are the lines to connect to the register chips, and this is the bus transceiver that connects the LCD display controller with the data bus. From the CPU's point of view, the LCD controller is just another port that is connected to the CPU, and there is a dedicated input and output port logic in my breadboard computer, which first allows selection of a port, so telling the port CPU interface which port should be talked to, and then the port can be addressed by simple port enable and port write control lines. And there are 4 ports in my build right now, which can be controlled with 3 CPU control lines, these port select, port enable and port write lines. And right now I only have 3 ports in use, and there is 1 additional spare port that is connectable to this CPU interface, but the whole thing is extendable to more than just 4 ports. You see there are 2 unused bits in the register, and you could connect more of those demultiplexers to access more ports. Actually, the LCD is on port number 0. The other ports are for the SPI bus and the keyboard. The port selector logic consists of 2 chips, whereas the first one is this 173 register chip. That chip latches a active port number from the data bus when the port select control line is active, and of those 4 select lines, only 2 are used to control this 139 dual demultiplexer, and depending on the active port number, whenever one of the port enable or port writes is active, it is forwarded to either the LCD display or the SPI bus or the keyboard controller. So from the software side, it might be interesting to know how to write a byte to the LCD display. As I use the 4-bit interface, the byte is sent in 2 half bytes, while the upper bits are sent first, so the bits 7 to 4 are sent first. And the step to send a single half byte is like this. You pull the read-write line low to tell that you want to write. Then you set the RS line to tell which register you want to write to, whether you're writing a command or data. And you set the data bits for DB4 to DB7 as appropriate to your byte. Then you pull the enable line high and the enable line low again. And you repeat that for the second half byte. This is the code to send a byte to the LCD display in my CPU specific assembly language. The byte to be sent to the LCD must be put in the A register, and this A register is the only register which is destroyed during this code is executed. The first thing we do is saving the interrupt inhibit state, because we set the interrupt inhibit state and then we restore it on return, so that the interrupt inhibit state is not changed during call and return of this routine. But I don't want to be interrupted during the byte sent to the LCD display, because it is sent in 2 halves and I don't want to be interrupted between the 2 halves of the byte. So the first half of the byte is isolated with this 4 bit shift instructions which shift the upper 4 bits into the lower 4 bits, and then we OR the state of the display backlight on off and put that byte on the LCD port. Then I enable the data, so this is the enable control line, and then I switch off the control line for the enable again, and then the same thing happens for the second half of the byte, which is already in the lower half. To receive a byte from the LCD display, you have to first receive the upper half of the byte and then the lower half of the byte. And the steps to receive that half byte, which also have to be repeated twice, are first set the read-write line high to signal that you want to read from the LCD display. Then you set the RS line, the register select line, as appropriate. So if you want to read a command, so state, or if you want to read data from the screen. Then you set the enable line high, and then you can read the first half byte from the DB4 to DB7 interface lines of the LCD display. And then you set the E line low again and repeat the same thing for the lower half of your byte. The function to receive a byte from the LCD display and returning it in the A register also starts by saving some data like the B register and the interrupt inhibit state, and then sets up the port to read from the display. The enable line is set high, and after that enable line is set high, the data can be read from the LCD port. And since we have the upper half byte first, we shift those 4 bits to the left and store the half byte in the B register, and then we read the lower half byte and OR it together with the already read upper half byte. This byte is then transferred to the A register and returned to the caller. Now that we are able to send data to the LCD display, the question is what does the LCD display do with this data? And first I want to describe how the command format works. The basic idea is this one command is 1 byte, and the highest bit set in that command byte determines the command type, and all the bits following this highest set bit may contain parameters. So you can see there are 7 0 bits and then a 1, and that is the command for clear screen. So the 1 that comes first is at the least significant position, so it is on DB0, and this means clear screen. So when DB1 is the first one in the byte, like this one, you see this is the cursor home command, which returns the cursor to position 1 1. Or you can see there is something like how to enter if the cursor runs, so the entry mode, like will the display be shifted to the left or to the right if you enter data, and so on. You can see the 1 that is the first in the command byte moves from the very right to the very left, so that the command with the longest parameter, like setting the cursor position, is the last command. Before the first character can be displayed on the LCD screen, there is a special kind of initialization that has to be done. And this is a sequence of commands where, first of all, we have to make sure that we are in 4-bit mode. And interestingly enough, the way to be sure to be in 4-bit mode leads over the 8-bit interface mode. So first one has to switch to the 8-bit interface, and that must be done again in case that we are in the 4-bit interface mode at the time that we try to switch, and because the system waits for 2 half bytes, we have to send the sequence switch to 8-bit interface twice. So in case we are in the 8-bit interface mode, it is switched to the 8-bit interface mode twice. In case we are in the 4-bit interface mode, it is switched to 8-bit one time. Then we explicitly switch to the 4-bit interface mode, which is an 8-bit interface command, and this is sent exactly once. So this is definitely just a single byte that is sent in total. And since the lower half data bit lines are tied low, it is sure that we have a definite value here. Then you should set the display mode like every other command that is coming now is a 4-bit interface command, so must be sent into half bytes. This is things like putting the interface in 2 lines mode and selecting the small font variation. Then you clear the screen so that you are certain which characters are on the screen at the beginning, and then you turn on the display, so make all the things on the display visible and set the cursor mode to say cursor on and cursor blink. Now that all the initialization has been done, we can write our first character to the screen, and all the characters are encoded in ASCII format, so capital letter A is on code point 65. There are some more special characters beyond point 128 which look like Asian characters to me, but there are also some European characters and some other graphical characters beyond that point. All the characters that you want to display on the screen have to be sent as simple data bytes. Be careful, there is a quite unexpected line configuration on the screen. That means we have 4 display lines on the screen which are handled internally as 2 lines, and the first internal line covers the display lines 1 and 3, and the second internal line covers the display lines 2 and 4. Because of the somewhat untypical line layout of the LCD display, the subroutine for displaying a single character is a bit more complicated as expected, because it has to follow the cursor position and has to adjust the cursor position whenever the last column is reached. So first of all, there were some special characters that are checked, like the backspace character or the new line character, and special treatment is done for these characters. In other cases, the display byte is sent to the display, and afterwards the cursor column is incremented. If the last column is reached, the cursor is put back 1 position, and then an explicit new line character is displayed, and this new line subroutine also handles the scrolling case in case that the last line was reached. Okay, the video is already long enough, so I don't want to speak about scrolling the display in more depth or about defining your own character sets or at least a few characters to extend the features of the LCD display. But I hope there was enough information to have an idea how to integrate an LCD display into your own breadboard build. As always, feel free to comment and hope to see you soon. Bye.